In section 5.3, we're going to be analyzing the graph of a rational function. So we're going to take everything we learned in sections 5.1 and 5.2 and put it all together into creating the graph of this rational function. So if you haven't already went back and looked at sections 5.1 and 5.2, now would be a good time to do so. The steps to analyzing a graph of a rational function are 6. The first step is to factor the numerator and the denominator and then find the domain. If 0 is in the domain, find the y-intercept and plot it. Okay, so let's start with step 1. Step 1, factor. So the numerator and the denominator are already fully factored. They're as simplest as you can be. However, we want to try to put these into reduced form, which eventually I will want to do by the time I get to step 3. But if I rearrange these, I can put x in front and x plus 2 on the bottom. Even if I pulled a negative out, it's not going to help me in reducing this. Because if I pull a negative out, well, that makes the 2 negative. So no matter which way I do it, I'll never be able to cancel something in the top with something in the bottom, because they can never be alike. So this is already in reduced form. So since it's already factored and in reduced form, what we're going to do is find the y-intercept. Remember, in order to find the y-intercept, we always set x equal to 0. Okay, so x equals 0. If we plug x equals 0 into either of these functions, we're going to get that y equals 2 minus 0 over 0 plus 2. In other words, you get 2 over 2, which is 1. So we'll have a y-intercept when x is 0, y is 1. So I'm going to go ahead and graph that on my graph, because I like to graph as I move through the information. So I have a y-intercept at 0, 1. The next step is to find the x-intercepts and plot them. So let's find the x-intercepts. Number 2. In order to find the x-intercepts, we set y equal to 0. So we have 0 equals 2 minus x over x plus 2. And if we set this equal to 0, this is a fraction that equals 0. In order for a fraction to be 0, it really doesn't matter what is in the denominator as long as the numerator is 0. Because theoretically, I could multiply both sides by x plus 2, and then you'll see that those are going to cancel, and 0 times x plus 2 is still just 0. So all I have is 0 equal to 2 minus x. So you can see that it doesn't really matter what is in the denominator, because in order for a fraction to be equal to 0, all you need is the numerator to be 0. Now if I add x to both sides, I find that x equals 2. So I have an x-intercept at 2, 0. So on my graph, I have an x-intercept at 2. The third step is to find any vertical asymptotes, which are the real zeros of the denominator, and graph them using a dashed line. So here I'm looking at the denominator, and I could clearly see for my domain says x cannot be negative 2. Because if x is negative 2, that makes my denominator 0. And since my domain says x can be any real number except for 2, that means I have a vertical asymptote at that place. So I'll have a vertical asymptote at x equals negative 2, which is going to be a dashed line. So on my graph at x equals negative 2, I'm going to have a vertical asymptote. Step 4 It says now find any horizontal or oblique asymptotes and graph them using a dashed line. Well, remember, in order to find horizontal or oblique asymptotes, we compare the degree of the numerator and the degree of the denominator. The degree of the numerator is 1. The degree of the denominator is also 1. So, since the degree of the numerator is equal to the degree of the denominator, that means we're going to have a horizontal asymptote located at y equals the division of the coefficients. So we're going to divide the coefficients that are in front of these x terms. So we're going to divide these coefficients. So it's -1 divided by 1. So we'll have a horizontal asymptote at y equals -1. So at y equals -1, we'll have a horizontal asymptote. If you have a horizontal, that means you do not have an oblique. Now, step 5, move the graph out of the way for a moment. Now, step 5 says to find any real zeros. So using any real zeros of the numerator and the denominator, divide the x-axis into intervals and determine where the graph is above or below the x-axis by choosing a number in each interval and then evaluate the function at that location. So if we look at our graph, I know I have a 0 at 2 because that's what makes my numerator 0. But also I'm going to have a 0 at whatever makes the denominator 0. So if we look at the numerator, we're going to have a 0 at 2. What makes the numerator 0? 2. And then if we look at the denominator, what makes this 0? -2. Okay? So we're looking at those as potential critical points that we need to focus on our graph. Because on our graph, those are critical areas. Because at +2, we have an x-intercept, and at -2, we have an asymptote. So those are going to be critical areas we need to focus on. So then we need to decide, well, what's happening to my graph on this side of the vertical asymptote? Is it below the x-axis, something coming around below the x-axis, or is it above the x-axis? And then in between -2 and 2, is it above the x-axis, or is it below the x-axis? And then on the other side of 2, is it above the x-axis or below? So knowing where it's at will give us a good idea of how to sketch this. So we're just going to look at this. This is the x-axis of this graph that I put off to the side. This is just the x-axis, just to get a cleaner view of what's happening around that x-axis. And we're going to test a point on this in each of these 3 intervals. So over here on the left-hand side in this interval, we're going to test the point x equals -3. And if I test this point -3 into this original function, all I care about is if we're going to get a positive or a negative number, meaning it's above or below the x-axis. So if I put in a -3, I have 2 minus -3, so that's a positive. And then I have -3 plus 2, which is a negative. So I have a positive divided by a negative, which ultimately gives me a negative, which means it's below the x-axis. In between here, let's test x equals 0. If I put in a 0, I have 2 minus 0, which is positive, 0 plus 2, which is positive. So ultimately, I'll be yielding a positive answer, which means it's going to be above the x-axis. This third interval over here, let's test, for example, the number 3. If I plug in a 3 here, 2 minus 3 is negative, 3 plus 2 is positive, and a negative divided by a positive is a negative. So my graph will be below the x-axis. So when I come back to my graph, I can finish sketching this. Because I know anything to the left of -2 is going to be below the x-axis. And I know it's not going to cross this horizontal asymptote. I know it's not going to cross this vertical asymptote, and it has to be below the x-axis. So the only choice for a graph over here would be to put the information down here. But if you weren't positive, you could always find a couple more points in the graph. If I know at -3, I know the actual value that it's going to yield. In other words, this would be 5 over -1, which would be a -5. I can plot that actual point. So at -3, -5, I know that that point's down there. And since I know it'll never cross either of those axes, or those asymptotes, I can assume that it's going to get closer and closer to both asymptotes. Clearly, you can also graph -4, -5, -6, -7, and find more points to be sure. So then I'm going to move over here to the space in between -2 to 2. We know it's positive, so we know it's going to be above the x-axis. So I could also graph this point here. We graphed when x was 0, and we knew when x was 0, we got the number actual +1, and that point is already on there. Since I know it's above the x-axis, I can assume that this is going to get closer and closer to the vertical asymptote. But now what's happening on the other side of 2? On the other side of 2, for example, when we tested the number 3 right here, we found that it had a negative value, which means it's going to come down below the x-axis, but remember, it can never cross this horizontal asymptote, so that means it must be getting closer and closer below the x-axis, but getting closer to that asymptote here. So this is what the graph of that function would look like. Let's do it again for another function. So the first step in analyzing the graph of a rational function is to first factor. Well, you can see that the numerator is not, or the denominator is not fully factored. This is the difference of two squares. So once it is factored, and then if 0 is part of the domain, find the y-intercept. So the y-intercept we find by plugging x equals 0 into the function. So that means 0, so y is going to be 0 over 0 plus 2, 0 minus 2. So that's 2 times -2. Well, 0 divided by anything is just 0. So I'll have a y-intercept at 0, 0, which is the origin. My second step is to find the x-intercepts. To find the x-intercepts, we set y equal to 0. So we set this whole function equal to 0. Now remember what I said with the above example, that if a fraction equals 0, it does not matter what is in the denominator. It could be 100, 1,000,000, or -4. As long as the numerator is 0, then the whole fraction is equal to 0. So all we care about is the numerator equal to 0. So that means x is 0. Which means, again, the origin would be our x-intercept. So let's go ahead and plot that point on my graph. This is the, oh, that would be upside down. There we go. The origin would be the x-intercept and the y-intercept. Step 3, now we're going to find the vertical asymptotes. Vertical asymptotes are located by graphing them with a dashed line. So what we want to do is find the zeros of the denominator after it's fully reduced. So this function is already fully reduced. Since it's fully reduced and nothing canceled, I know my domain has exclusions where x cannot be -2 or 2, because that would make my denominator 0. So that means I'm going to have vertical asymptotes at those locations. So at x equals 2 and x equals -2 will be vertical asymptotes. So I will put those on here with a dashed line. So at x equals 2 and x equals -2. In step 4, we'll now find any horizontal or oblique asymptotes. Horizontal and oblique asymptotes are found by comparing the numerator and the denominator exponents. The numerator exponent is 1, and the denominator exponent is 2. Since the numerator exponent is less than the denominator exponent by 1, it's a proper function, it's a proper fraction. That means automatically I will have a horizontal asymptote located at y equals 0. Whenever n is less than m, you will have a horizontal asymptote at y equals 0. So if I graph that, y equals 0 is the x-axis. There is no oblique. You cannot have a horizontal and an oblique at the same time. You can only have one or the other. Now, I don't think this is enough information to graph yet. I clearly don't know what's happening in any of these 6 different quadrants. So what I'm going to need to do is find some test points to find out what the graph is doing. And that's what I'm going to do in step 5. So in step 5, I'm just going to graph the x-axis and find some test points. I know I want to break this up into intervals at what makes the denominator 0, which is clearly -2 and 2, but also what makes the numerator 0, because sometimes that can also be a critical point that we want to analyze. So I'm going to test 1, 2, 3, 4 different intervals with different test points to see what's happening in each of those intervals. So I'm going to test on the left, I'm going to test the number -3. When I plug -3 up into my function, I have -3 over -3 squared, which is 9. 9 minus 4 is 5. So I have -3/5. So when x is -3, y is -3/5. Clearly, when you put in a -3, you're going to get an answer that will always be below the x-axis. So on my graph, when I graph that over here, anything to the left of -2, you're going to get something that's below the x-axis down here in the 4th quadrant. If I test this point, -3, -3/5 is like right there, and everywhere in this interval is going to be below the x-axis. It's never going to go above this horizontal asymptote. So it's clearly going to hug both of those asymptotes. So now let's move over to this interval inside. Let's test the point x equals -1. If we test x equals -1 for y, we're going to get -1 divided by 1 minus 4, which is -3. This is actually a positive number, so it'll be above the x-axis in this interval. So if I plot this point on my graph, so at -1, we'll have a y of 1/3. So at -1, 1/3. So everywhere between -2 to 0, it will be above the x-axis, so that means it's going to be hugging this vertical asymptote. But now on this side, I don't know if it's going to continue down or if it's going to continue and go back up like a parabola. So that's why we have to test now a number in here, like the number 1. So now let's test the number 1. And when I plug that into my original function, I have 1 divided by 1 minus 4. 1 minus 4 is -3. So I actually get a negative number, which means it's below the x-axis. So that tells me then that this graph, since it is below the x-axis, is going to continue down and hug that vertical asymptote down towards -infinity. Now my last piece is going to be over here. It's either going to be a C in the 1st quadrant or a C in the 4th quadrant. So we're just going to have to do one test point to see if it's positive or negative to see where that's going to go. So let's go back over to my x-axis and let's test x is 3. When I plug 3 into my original function, I get 3 divided by 9 minus 4, which is 5. So I get y equals positive 3/5, which is above the x-axis. So to finish out my graph down here, to finish off my graph, I have a point at 3, positive 3/5. So that means everything in this area will be above the x-axis and look like that. So we're going to do 2 more graphs. 2 more graphs. We're going to analyze using all those steps.